So today we're going to talk about partial derivatives. So this is how we take derivatives when we have functions of more than one variable. The partial refers to the fact that we're dealing with one variable at a time rather than all of the variables. So let's start by reviewing how we came up with derivatives and what they're used for with single variables. So we came at this problem by saying we wanted to find a tangent line to a function at a point a comma f of a. And we did this by approximating it with secant lines. So for instance, here we can see the red lines here are secant lines approximating the tangent line there to this curve at 1 comma 1. So you can see as the dot on the right side moves closer, the secant lines become a better and better approximation for the tangent line to the curve at that point. And the slope of the tangent line was what we defined our derivative to be. So we see the slope of the secant line through the point a comma f of a and a plus h f of a plus h is just the change in y over change in x. We have two points. We're finding the slope of the line between those 2 points. So change in y over change in x. So we get f of a plus h minus f of a over a plus h minus a, which just gives us an h in the denominator as the a's cancel out. So we see that as the secant lines the h got smaller and smaller on the previous slide, the secant lines became better and better approximation for the tangent line. So that means if we let these h's get smaller and smaller, this should end up giving us the slope of the tangent line. And that's how we define the derivative. The limit as h goes to 0 of f of a plus h minus f of a over h. So now what we want to do is we want to apply this same concept to functions with more than one variable. So let's start with just saying we have a function z equals f of xy, so just a function of two variables. And for illustrating this, we'll consider the function z is equal to 10 minus x squared minus y squared. So this is our surface we're looking at. So what we can do here is we can fix the value of y0, and then we can view z as just a function of x, because now x is still allowed to change, but the y is not changing. Y is staying as y0 all the time. So if we look at this, if we were to plug in y0 or y equals y0, which is 2 here, we would get 6 minus x squared. And we can see that pictured on the 3D graph here is this red curve. So this is the curve z of x equals f of x comma y0. Okay, so this is the curve f of x comma 2. We can now, since z is now being just a function of x because we've fixed y, we can ask, well, if we change x, how does z change? So let's consider this quantity where we're letting x change by h and we're leaving y fixed. So if we look at this, this looks very familiar because it looks just like the derivative of a function of one variable. We just happen to have that second variable there that's not moving. And so if you look at the curve that we had before, that red curve, this value here is exactly the slope of the tangent line to that curve. So here the tangent line to the curve there is given in blue, and so the slope of that line is the limit as h goes to 0 of f of x plus h comma y0 minus f of x comma y0 over h. So we define the partial derivative of z with respect to x at the point x0, y0, and we write it with this curly d here, which is called del. So we say the partial derivative of f with respect to x on the left-hand side is just this limit where we're only letting the x variable change and the y variable is fixed. And so we can also view this, just as in the one variable case, we can view it as a function of x and y if we like, rather than just looking at it as a single point. And in this case, we just use x and y. But still notice that in the right-hand side of this limit, the y is still staying the same. We have f of x plus h comma y minus f of xy over h. The y is the same in both terms. So we're still only varying the x, even if we're letting x and y be variables here. And then, of course, there's nothing special about x. We can play the exact same game we did with y, where we just fix a value of x instead. So if we fix x to be 2, this is what the curve would look like now. You see this orange line here is where x is equal to 2. And here's the tangent line at that case, is this purple line. And so we say the same definition here. We would just let the y's change and the x would be fixed to get the partial derivative of f with respect to y. So notice we get lots of tangent lines here. So we've only pictured 2 tangent lines, but there's really one in every direction that we might want here, not just changing x or just changing y. We could let each of them change in a different direction. And so what this will give us is, this actually gives us a tangent plane to the surface. So we saw when we had functions of one variable, we had a tangent line at any particular point where the function was differentiable. For us now, if we take any particular point on a surface where the function is differentiable, that's going to give us a tangent plane. We'll come back to this. So we don't have to stick to just 2 variables. There's lots of things that vary in terms of several variables. So we can do the same thing and we can define a partial derivative, just like we did for 2 variables, for any one of the variables here, x1 through xn. So if we pick any particular one, say xj, it's the same definition here where we're only letting the xjth term change and all of the other terms stay exactly the same. So the nice thing about partial derivatives is they're actually really easy to calculate as long as you know how to take derivatives of functions with one variable. So if we recall how we just defined this definition, or this concept, is we let one variable change and just kept the other one fixed. But then the definition was just the exact same as the definition of a function, a derivative of a function of one variable. So that's how we do it. We just differentiate the function with respect to the variable that's changing and treat the other variables as if they're constants. So let's see an example. So let's let f of xy be x squared y plus cosine y squared. And we're going to take the partial derivative of this function with respect to x and with respect to y. So first, with respect to x, notice the cosine y squared has no x's in it, so that's a constant in terms of x, so that will go away. In the first term, x squared y, y is treated as a constant there as well, so that'll just become 2xy. So our partial derivative with respect to x is just 2xy. And if we do with respect to y, now the first term, the x squared, is constant, so we take the derivative of y, which is just 1, so that leaves us with an x squared. And for the second term, we have cosine of y squared, so we need to use chain rule for this. So the derivative of cosine is negative sine, and then the derivative of y squared is 2y. So our partial derivative with respect to y is just x squared minus 2y sine y squared. So it is customary to use this subscript instead of writing out the whole thing each time, kind of how we used f prime of x when we had one variable to save writing df dx all of the time. Here we write f sub x and f sub y because we can't just write a prime here because we have to indicate what variable we're actually taking the derivative with respect to. Now we also saw when we used functions of one variable that the second derivative could be really important for different setups. For instance, if we had our function was a position function, its first derivative was the velocity and its second derivative was acceleration. So we can do the same thing in this case, is if I take a partial derivative of a function of 2 variables, say, with respect to x, I can then take this partial derivative of that function, but I could take the partial derivative with respect to x, with respect to y, and so we get more partial derivatives than we just a single second partial derivative. So we see here, here's our notation. So f with a subscript xx is you take the partial derivative first with respect to x, and then whatever function you get out of that, you take the partial derivative of that with respect to x. And you can see this reflected also with the partial, the curly d's here as well, the partial derivatives in that notation. You first do inside the parentheses here, so you take the derivative with respect to x, and whatever you get out, you take the derivative of that with respect to x. Same exact thing with y here. The only difference here is now we get what are called mixed partial derivatives, because first I take the derivative with respect to x, and then with respect to y. And so you see, in this case, the order here makes a difference because it's first x and then y, so you get the dy dx here. And if you do y first and then x, it's this notation. So if you have 2 variables, there's already 4 different second partial derivatives you can have. The more variables you have, the more partial derivatives you have. And as you go up, if you take another partial derivative, so you take the third partial derivative, there'll be even more partial derivatives. So you can see it kind of escalates quickly with taking these partial derivatives. So let's come back to an example again. So in this case, we're going to let f of xy be x squared cosine of y plus sine of x. So we take the partial derivative of this with respect to x and with respect to y. So with respect to x, the first term becomes 2x times cosine of y, and then the derivative of sine is cosine. If we take the derivative with respect to y, the first term becomes minus x squared sine y, and then the sine of x is constant with respect to y, so that just becomes 0. Now we take the second partial derivatives of all of this. So for the first one, we're going to take the derivative of this top term with respect to x. So this x will become 1, so I'll get 2 cosine y. And then the derivative of cosine is minus sine, so I get a minus sine here. When I go to this one, I take the derivative with respect to y. The x squared is constant, so it's just the derivative of sine of y, which is just cosine of y. And then finally, if I take the derivative of this one with respect to y, I'm going to get a minus 2x sine y from the derivative of this part. And then this is constant with respect to y, so that'll go away. So I get minus 2x sine of y. And then if I take the derivative of this with respect to x, the sine of y is constant. So I just get a minus 2x sine of y. So what we can notice here is that those mixed partial derivatives, the f sub xy and the f sub yx, those are actually equal in this case. And it turns out it's not a coincidence that that's the case. This happens more generally. So if we take a function f of xy and a point x0, y0, if all of the second partial derivatives are continuous for all of the xy's in a small disk around x0, y0, so think of any, basically draw a circle around x0, y0 in the xy plane, and you can make that circle as small as you want, but you do have to have that those second partial derivatives are continuous for all of the xy's in that really small circle you draw. If that's the case, then those mixed partial derivatives are actually equal to each other, which makes it nice. You don't have to calculate each of them separately then, you just know they'll be equal. And that's it for partial derivatives for now. This gives you the basics. Obviously, we'll cover more advanced topics with partial derivatives in class.